had discussed about vector space, and today I will discuss spaces of vector space. Subspaces is a smaller set within a vector space V that is itself a vector space. Here every element of U is also element of the original vector space V. To satisfy this subset U is a vector space, we have to satisfy U is closed under addition and multiplication. Definition is such type subspace U of a vector space V. Obviously this is subset, and this subset is such type. Consider two arbitrary vector U and V belongs to this subset U and C belongs to a real number, then 0 vector always contained in this subset U and U plus V always contained in this subset U, means this subset is closed under addition, and CU always contains this subset. That means this subset is closed under multiplication, and this is the definition of subspace. That means always 0 contained in this subset, closed under addition and closed under multiplication. As for example, consider the vector U equal to, say those contain A3A where A belongs to real number is a subspace of R2. For this, we have to check if U is a subset of R2. Obviously, this is subset of R2 because this contain those set which contain A and 3A where A belongs to real number. Next, we have to check is the vector 0 contained in the set U. Obviously, this is true because when A equal to 0, then 0 3A would be 0 0. Obviously, this belongs to U. Then we have to check if U1 U2 belongs to the set U. Then is there sum belongs to the set U? Consider U1 equal to A3A and U2 equal to B3B. Then their sum would be A plus B, 3A plus B. Obviously this is belongs to U. Next, if U belongs to U and C belongs to real number, then CU belongs to the set U. Obviously, because C times A3A would be CA, 3CA. Obviously, this is belongs to U. One new type of question. What will be subspace of R2? Here, at first consider the line which does not take the origin. If we take two vector, then there are some still be in this line. This is true, but this line does not contain the 0 vector. The line which does not contain the origin not be subspace of R2. But if we consider the line which is through the origin, this is obviously subspace of R2. This line contains obviously 0 vector, and if we take 2 vector, then there some still be in this line. Also, multiply this line by a scalar. Also, this still be in this line. Okay? So, line through the origin always be subspace of R2. Now, consider this plane in R2 Is this vector space? At first think. If we take one vector and multiply this vector with a scalar c, then this line exits this space. So this plane not be subspace of R2. But if we take this whole plane, then this is obviously subspace of R2. That means the subspace of R2R, whole R2. Second, when W subset of V, then only the vector which contains 0, this is one subset, other subset. When W not equal to 0, then the line passing through origin, that means those line which passes through the origin, then this is also subspace of the vector space R2. Consider the space V equal to R3. Here the subspace R1, the set which contain only 0 vector, and line passing through origin, also the plane which passes through origin. That means here the plane passing through origin means x plus by plus cz equal to 0. That means set of those vector x, y, z belongs to W such that ax plus by plus cz equal to 0. That means in R3 there exist 3 subspace. Okay? Are you getting? Well. Now consider a subspace in Rn. Here the space is Rn and fix 1 less than equal to m less than n. And consider the subset W equal to x equal to x1, x2 up to xn such that xi equal to 0 for all r greater than equal to m. Here xi equal to 0 for r or r greater than equal to m means here non-zero point x1 up to xr minus 1, and after that the value would be 0. Now we have to check, is the set W is a subspace of Rn? Let's check. For this, here the element is look like x1, x2, non-zero is up to xr minus 1, then after r all point be 0. Consider this is x which is equal to this and this point be y. Then their sum would be x1 plus y1 up to xr minus 1 plus yr minus 1, then after that all point be 0. And obviously this is member of W. Also if we multiply c times x1 up to xr minus 1, then after that all the point 0, then this would be cx1 up to cxr minus 1, then after that all the point be 0. Obviously this is also belongs to W. That means the set W is a subspace of Rn. Are you getting? Well. Consider different type of subspace. Here the space defined as set of all function which is defined from closed interval AB to AB. And consider the subset W1 as set of all function which is defined from closed interval AB to AB. Now my question, is W1 is a subspace of the space V? That means, is set of all continuous function be subspace of set of all continuous function? Because here the vector space is set of all function which is defined from closed interval AB to AB. And this is obviously true. Because obviously here set of all continuous function from AB to AB, obviously this function contain zero function, and sum of two continuous function always be continuous. So this is closed under addition. Also, if we multiply any function by scalar, then also this would be member of W1. That means this is closed under scalar multiplication. So set of continuous function who is defined from closed interval AB to closed interval AB always be vector subspace of the set of function who is defined from closed interval AB to closed interval AB. Now consider the new set W2, who is be the set of all differentiable function who is defined from closed interval AB to AB. Obviously, this is also vector subspace of V, because sum of differentiable function always be differentiable function. Also, if we multiply any differentiable function by a scalar, this is also differentiable function. Also, W2 be the vector subspace of W1, because differentiability always stronger condition. All continuous function always not imply the function be differentiable, but all differentiable function always be continuous. So W2 be the vector subspace of W1. Now I will define the new type of set. X be any set and function defined from X to R. Now consider B of XR, which is set of those functions such that f is bounded on the set X. Prove vector subspace. Obviously B of XR be the subset of f of XR, and zero function always be member of B of XR. Consider two arbitrary function f and g belongs to B of XR. That means there exists a constant m1 such that for all x belongs to capital X, absolute value of fx less than equal to m1. Also, there exists a m2 such that for all x belongs to capital X, absolute value of gx less than equal to m2. Okay? And for all x belongs to X, absolute value of f plus gx equal to, by triangle inequality, this is equal to fx plus gx, which is less than equal to mod fx plus mod gx, and mod fx less than equal to m1 and mod gx less than equal to m2. That means this is less than equal to m1 and this is less than equal to m2. That means sum of this function obviously be member of B of XR. Similarly, absolute value of C fx would be absolute value of C times absolute value of fx, and this would be less than equal to fx less than equal to m1. This would be less than equal to absolute value of C times m1, which obviously belongs to B of XR. That means set of all bounded function obviously vector subspace of set of all function who is defined from X to R. Consider new type of subspace. Here the vector space is set of all real sequences and be equal to the set of all bounded sequences. Similar to set of all function, here only defined set of real sequences. Similar to before, this is B obviously subsequence of set of all real sequences. Now consider new set gamma, who is defined set of all convergent sequences. This is also vector subspace of set of all real sequences. For this, consider two sequence an and bn such that these two sequence belongs to gamma, and since this is belongs to gamma, then obviously an converges to a and bn converges to b. Now we have to check Gamma is a vector subspace of set of all real sequences. For this, an plus bn obviously equal to an plus bn. And since an converges to a and bn converges to b, that means this is equal to a plus b. Therefore, an plus bn converges to a plus b. Okay? That means gamma also be vector subspace of set of all real sequences. And this set gamma also be vector subspace of set of all bounded sequences, because set of all convergent sequences always be bounded, and this is vector subspace of f of xi. Similar to before this, here only real sequences function as real sequences. Now consider other vector subspace gamma naught, which is defined as set of all sequences such that limit of these sequences equal to 0. And obviously gamma naught is vector subspace of gamma, and gamma obviously vector subspace of beta, and this is vector subspace of main sequence set of all sequences. Okay? Consider another new vector subspace. This is set of all sequences such that there exists a capital N such that an equal to 0 for all n greater than equal to capital N. Obviously this is vector subspace because if you consider A equal to A1, A2 up to A100, after that all term be 0. Also if you consider other term B equal to B1, B2, here consider B50, after that all term be 0. And obviously A plus B belongs to gamma naught, double naught. Similarly, if we multiply any scalar, this is also belongs to gamma double naught. So obviously this is vector subspace. That means there exist various type of vector subspace. Gamma double naught be vector subspace of gamma naught be vector subspace of beta, set of all bounded real sequences. Sorry, here gamma, set of all convergent sequences, and this is vector subspace of set of all bounded sequences, and set of all bounded sequences be vector subspace of set of all sequences, which is denoted as f of xi. Are you getting? This is very interesting type. Now consider new type of vector space here, set of all n cross n real matrices. Here I will see many vector subspace of set of all n cross n real matrices. What symmetric matrices over the field are? Obviously this is vector subspace of set of all n cross n real matrices, and similar to before, skew symmetric matrices also be vector subspace of n cross n real matrices. We consider all scalar matrices, that means lambda times I, where all lambda belongs to R. This is also vector subspace of MNR. Also, if we consider all upper triangular matrices, these would be also vector subspace of MNR. Similarly, all lower triangular matrices or diagonal matrices all be vector subspace of set of all n cross n real matrices. That means for n cross n real matrices there exist various type of vector subspace. We will see new type of vector subspace. Here V is set of all polynomial whose degree less than equal to 4, and the subspace is denoted as set of those polynomial belongs to this polynomial whose degree less than equal to 4 such that p minus 1 equal to p0 equal to p prime 1 equal to 0. That means at those point this polynomial has a root. To show W is a subspace, at first we have to show, we all of us know it contains 0 vector closed under addition and closed under scalar multiplication. Here obviously the subspace indicate p minus 1 equal to p0 equal to p prime equal to 0. That means obviously this subspace contains 0 vectors. That means option 1 is right. Now we have to prove closed under addition and closed under scalar multiplication. Combination of these two results to prove vector subspace easily would be lambda g plus mu is x belongs to V, where lambda and mu belongs to field. Here the field is real number and G is V, member of vector space. That means polynomial degree less than equal to 4. To prove vector subspace easily, this is one method. If we can find lambda g plus mu is here polynomial, so here x belongs to V, so obviously this subset be vector subspace. Now we have to check for this point x equal to minus 1, x equal to 0 and x equal to 1, this polynomial, this type of polynomial belongs to vector space. For x equal to, if we consider at first x equal to minus 1, then lambda g plus mu is times minus 1 polynomial, this is obviously equal to lambda times g minus 1 plus mu times h minus 1. The subspace indicate as polynomial at the point minus 1, the value is 0. That means this value would be lambda times 0 plus mu times 0, which is equal to 0. That implies lambda g plus mu is obviously belongs to W, because at the point minus 1 this type belongs equal to 0. Second, we have to check for x equal to 0. For x equal to 0, lambda g plus mu is here at the point 0, this is equal to lambda times g0 plus mu times h0. This is obviously g0 equal to 0 and h0 equal to 0, this is obviously 0. And since similar to before, lambda g plus mu is at the point 0, this value is 0, that means obviously lambda g plus mu is belongs to W. We have to check the derivative function at the point 0. That means lambda g plus mu is prime at the point 0. This is equal to lambda g prime 0 plus mu is prime 0. And obviously this value equal to 0 given plus mu times 0, which is equal to 0. That implies lambda g plus mu is prime obviously belongs to the set W. Therefore, all condition has satisfied here. Therefore, this subspace W is a vector subspace of set of all polynomial whose degree less than equal to 4. Are you getting the method? This is the shortcut method to find the vector subspace. This is just combination of these two methods. Today I will stop here. In my next video, I will discuss other topic of vector subspace. Vector subspace is very important to understand the vector space deeply. So at first I will highly recommend you, please see today's video with pay attention. See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel for more videos. Thank you so much.